Welcome, everybody. Welcome, everybody. So I wanted to record my lecture to make sure that we have finished the entire section before we assess on Monday. Great job. I know this is a big unit. Let's get right to it. So we're done with a bunch of different sections. There is a math section on the AP Environmental Science exam. One of the reoccurring themes that pops up is something called percent change. Percent change, depending on your math teacher, probably showed you a particular formula. I'm going to teach you a different formula that really works well for the AP Environmental Science exam. The only trip is that it may not tell you directionality if it's going a percent increase or a percent decrease. It's really like a percent change. The AP exam will ask the direction if it's an increase or a decrease. So you'll get some data, and usually like 2 dates of data. So let's just say, and let's use some easy numbers here. Let's just say where's something that is exactly on 2. Okay, we could use, let's just use these numbers right here. Let's just say this is 5. In 1997, what did the data give you? And let's just say this is 5. That would be the initial. You're going to minus that from the final. And so in this case, let's say, so if we were doing 1997, I know it's not exactly 5, but this is just an example. Let's say it's 5. And then what was the percent change from 1997 to 2008? And let's just say this is 2. So this would be 5 minus 2. In that case, that would be 5 minus 2 is 3. So now you have 3 on the top here, and you're going to divide that by the initial, which was 5. So if you do that, you pop that into a calculator, and then you're going to multiply that by 100. Not 100%, you're going to multiply that by 100, but then that is going to equal a percent. It's kind of weird there, okay? You're going to multiply it by 100, and then just add the percent sign to it, okay? That's going to be your percent change. In this case, you'll have, since you're going from 5 to 2, you have a percent decrease. This is used multiple times, and we'll have some more practice later on. And it could be used multiple times in multiple different subject materials. For instance, we could say CO2 levels from 2005 to 2020. The percent of cell phones being recycled, we could use that. We could say, 10 metric tons to 15 metric tons. We could use percent change in many different aspects of the AP exam. So make sure that you pay attention to this formula and practice it. And you can make up your own questions to practice it your own. Now let's go to our next slide here. So another thing that we need to discuss is productivity. And when we're talking about productivity, what we're really talking about is the amount of photosynthesis that's going on in an area. And then when you really think about it, right, it's the sun's energy that's getting captured by the producers, the plants. Then organisms eat the plants and they're getting that energy. So if the plants get that energy from the sun, then ultimately all of us get our energy from the sun. That just actually makes us think like we're just like Superman. Didn't Superman get his energy just directly from the sun? Okay. Now, how does that work in a food chain? Well, the first one is a little tricky. The first primary, these photosynthetic organisms typically are only going to get 1% of the total units of energy from the sun. So for instance, if it was 100 units of energy focusing on this plot of land, then that's only 1% that's going to go into those plants, the plant tissues. 99% of that is gone. Okay? That's only the first trophic level, though. There's something called the 10% rule, and that is each subsequent trophic level as you go up. And notice in a food chain, you're never really going to go further than 5 trophic levels or maybe 6 trophic levels. And I know you could say humans could eat anything, but in reality, we hardly ever go to a fifth or sixth trophic level. The reason why is that the amount of energy decreases as you go up each trophic level. So in this case, let's just say, and if we're talking about that first trophic level, only 1%. And let's just say, I don't even know. I mean, I don't, the number in my head can't be big enough. So I don't know what 1% of 1,000 pounds of energy would be looking like. So let's just say the first trophic level has 1,000 pounds. Okay. Now, the next energy level is all we have to do is move the decimal over one to the left. And when that happens, now we're only at 100 pounds. We do that again to the next trophic level. We have 10 pounds. We do that again to the next energy trophic level. We only have 1 pound. So we're losing 90% of that energy. 90% of that energy is lost. Well, where does that energy actually go? Energy cannot be created or destroyed, but it's used up. It's used up as heat energy. Okay? That's the second law of thermodynamics. The first law is energy cannot be created nor destroyed. The second law is entropy is always increasing, which basically means that energy is being used up as heat. So these organisms are using a lot of energy as they're digesting, binding, and eating this grass, and that accounts for that 90% of that energy loss. Now, once again, the first energy trophic level from the sun, if I were to give you a problem with the sun's energy, you would take 1% of that. Each subsequent energy trophic level is only going to take 10%. Understand, as you go up the trophic chain, you're going to have less and less energy. And so the question on our homework was, why doesn't a line eat another line? Well, first off, that line would be up here. And if it was on another trophic chain, there'd be so little energy that it wouldn't be worth the lion's time to actually eat another lion. Plus, it would risk injury. It would possibly lose more energy. Let's say if that lion only had 10,000 calories, but I'm using 20,000 calories to kill it, well, then that doesn't make any evolutionary sense. It will not happen. Okay. A review of some vocabulary. These are producers, primary producers. First order consumers, also known as primary consumers. Secondary consumers, tertiary consumers. You could use every single term to try to describe these. Another thing that typically people don't feed past the fourth or fifth trophic level, or even organisms. Well, I wouldn't say organisms don't do this, but I would say people. It's not necessarily healthy to eat all the way on the top of the food chain, and let me explain why. Large fish would potentially have many different heavy metals that have been acquired throughout their lifespan. If you saw that movie Dark Waters, they were talking about a term bioaccumulate, and toxins can accumulate over a lifetime. So you never really want to have or eat a very big fish. They may have a lot of lead or mercury stored in their tissue. And when you eat that, you may actually get some lead and tissue inside of yourself. Think about it, right? In order for that fish to get so big, it must have eaten a lot of smaller things. Those smaller things eat other things, and those smaller things eat other things. Each while, even if one of those little fish had a little bit of poison in it, but if I eat 1,000,000 fish over my lifetime, then I'm probably going to have a lot of those poisons and toxins in my body as well. So it's not probably really smart to, you could eat bear, but it's probably not the smartest to eat a bear, a polar bear. It's probably not the smartest thing to do. And they recommend that women don't eat large fish on a daily basis because there could be a concentration of lead that builds up. And every day you eat it, you could get more and more exposure to it. And you don't just poop it out. Sometimes it stays in the fat of the tissues. All right. So fat soluble heavy metals will stay in your body the longer you live. So, the longer you live, these toxins kind of build up in the body. All right. So for this right here, we've learned the 10% rule. You should be able to calculate, well, if the first energy level had 10,000 units of energy, how much would the fourth trophic level have? And all you have to do is move the decimal over to the left one time. If I gave you the amount of energy in a given area, you would take from the sun, you would take 1% of that and put it into the producers and then do the 10% rule further up. So going back to that term primary productivity. that term primary productivity really reflects how much energy or photosynthesis is going on. And so here is a pretty good diagram that tells you in comparison to other places. So look at this. You have a estuary, swamps and marshes. There's a lot of photosynthesis going on over there. And notice these are over the tropical rainforest, but these are more aquatic ecosystems. So you can't say, you know, the tropical rainforest isn't the one that has the most primary productivity. It does. But estuaries and swamps and marshes are also going to contain a tremendous amount of primary productivity, a lot of photosynthesis. And then we get all the way down to the desert, very little. Now, what's funny is that in open oceans, pay attention to this, I don't think I've gone over it. Open oceans do not necessarily have a great deal of plants and animals and so on and so forth, or photosynthetic. They do have photosynthetic organisms, but they're not like in close proximity with each other. They're more dispersed. However, if we looked at overall, where does most of the photosynthesis occur on our planet? It actually occurs in the ocean. It occurs in the ocean through those cyanobacteria, those photosynthetic bacteria, that phytoplankton, that is dispersed in our ocean all over. And the reason being is most of it occurs because there's just so much ocean. Like we discussed before, 70% of our planet is covered with ocean. So the ocean is very vast. The ocean is very big. And even though it's not very dense, but since there's so much of it, the overall photosynthesis occurs most in the open ocean. I've seen this question often, so make sure that you understand that you have to take into consideration the vastness of the ocean for the overall amount of photosynthesis that goes on. Go to our next slide here. Okay, so 10% rule again. And notice when we talk about this energy over here, okay, 1% of the solar system's energy is in here. Okay, so I guess if I added 2 zeros, I could tell you that that's how much energy that was coming from the sun, and this is how much energy that actually got absorbed by those producers. Notice now we're just moving the decimal over 1, so now there's only 1,000 kilocalories of energy. We'll move the decimal over 1, we have 100 kilocalories of energy, and now we have that tertiary consumer only having 10 kilocalories of energy, right? So this is that 10% rule. It's something that appears often on the AP exam. And once again, where's that energy going? Well, that energy is going as heat energy. That heat energy can't be used again, okay? It basically flows out of the universe, okay? That energy is just gone. It goes back into the universe, right? It can't be reabsorbed and used again. It literally leaves. As far as energy on our planet, different from matter, it's like an open system, okay? So we'll just leave it at that. Once again, I think we're over here with a practice problem, and I really have to apologize for this nonsense that goes on. Maybe I don't need my face. Oh, gosh. So let's look at a practice problem using the 10% rule. Once again, we're just moving. Oh, this is a great slide because this is going to show you exactly, this is how much joules of sunlight is coming from the sun. Well, how much is captured into this first trophic level? And so here I would actually move the decimal over twice because it's only 1%. So I only have 10,000 joules of energy, and then we just move it 1 each subsequent level. Okay, so here you can do a ratio, right? You can do a ratio to try to figure out this answer. And so with this one, you would say you would have 34 frogs over 300 and, yes, you would have 34 frogs over 340 grasshoppers, and you could set that up. And then you have a multiplication sign, and then you're going to have how much grass, okay? And you'll put the grass as the grasshoppers on top as 340, and then have X underneath there. You cross multiply and divide, and that's how much grass you would need to feed the grasshoppers. All right. Now, in the next one, we're going to give you how much energy is shining in a particular area. Okay. Now, look at this. This is 10,000 kilocalories per meter square per year. This is how dimensional analysis works, and this is how sometimes these questions get tough. So let's try to pay attention here. So this is 10,000 kilocalories per meter square per year. It shines down on a 10 meter square forest ecosystem. Right. How much of that energy enters the first trophic level? Well, let's look at this. This is crazy. First off, we get 10 per meter square, so we have to multiply this 10,000 to 10, so we're going to add a 0 here. So that would give us to 100,000. However, how much does it enter the first trophic level? Well, now we're going to take 2 steps back, so it would be 1,000 units of energy, or 1,000 kilocalories of energy in that first trophic level. And then we could go each subsequent level up there. That's what problems look like, all right? And if there is any questions in regards to you quite don't understand it, I think we could possibly arrange some time where we could speak in private, all right? Let's continue. Like we talked about before, we have that first and second law of thermodynamics. Energy cannot be created nor destroyed. It simply changes form. And I want you to think of it. Sunlight energy turns into chemical energy, glucose energy. I eat the plant, I get that glucose energy. Okay, I could store it as fat, or I could use it as mechanical energy, and then I produce heat and steam, and now we have that heat energy that's leaving my body and basically going out into the universe. And so entropy is that non-usable energy. So what we really say is that the fixed amount of energy in our planet, the usable form, the beautiful form of energy, is slowly turning into non-usable form of energy, aka chaos. Okay, so beautiful sun gives us usable energy, and then it just transfers ultimately, after it goes through the ecosystem, into something totally different. Okay, we have some vocabulary here: primary producers, primary consumers, secondary consumers, and then tertiary consumers. All right, know that vocabulary. Also, know these different types of energies. Okay, potential energy, that's stored energy, glucose by itself. Kinetic energy, me using that, okay? Me using that or moving. Solar energy coming from the sun, thermal energy, heat energy itself, mechanical energy, something that's made by a machine, and then finally a chemical energy, a type of stored energy. Right? This is just basically giving you some vocabulary to understand that energy cannot be created or destroyed. It simply changes its form. Right? Here we have a hard problem. It's another math problem. Let's take our time with this really quick. Okay. Terry had a 2,000 watt hair dryer, and he used that for 4 hours a day. How many kilowatt hours did he have? Okay, so let's see how we're going to answer this. Okay, so how do I solve something like this? Well, we have 2,000 watt hair dryer, and energy is typically measured in kilowatt hours. That's how much you get charged by the electrical company. So if I use that 4 hours a day, well, how many did I use them per day? Well, 2,000 times 4 is going to give us 8,000 watts, but I want kilowatts. So how do I convert 8,000 watts into kilowatts? Well, please understand that you need to do some conversions, and we'll probably have a page on math to do that. And if you remember meters to kilometers or kilometers, well, basically 1,000 watts is equivalent to a kilowatt. So what we're going to do is use a conversion factor, and that'll give us 4 kilowatt hours per day. Now, if I use that 4 kilowatt hours per day, and then the question is how many kilowatt hours per year, I would have to multiply that by 365. In science, you have to always, or in our test, you have to always show your math. Okay? You have to show your work, right? Even if you have to type in the formula, even if you're going to write your answers and then take a picture of it, you have to show your work. If you don't show your work, it's marked incorrect. If you don't use your units, it's incorrect. Okay? And even if you got the right answer, no units, no points. This is how the rubric works. And it's very frustrating, but it happens. Okay? So for right now, we're at, it was 2,000 times 4, and that's 8,000. And then we have to convert that into kilowatts. That's 8 kilowatt hours a day. And then that 8 kilowatt hours per day times 365, that's going to be a bunch of kilowatt hours. I may then have to convert to something called BTU, and that's just another unit of energy. So I use a conversion factor of 1 kilowatt hour is equivalent to 3,412.14 BTUs. And then I would get a number there. Then if I wanted to convert that into a cubic foot of gas, we would use 1,000 BTUs. A conversion factor of 1 cubic foot of gas is equivalent to 1,000 BTUs of energy. I could set that problem up and I would get my answer. You should probably pause this, go back and forth to try to understand what I'm saying. One thing you need to understand is conversion factors. Kilo to regular is one of those factors, okay? Then, if you understood what a conversion factor from chemistry is, you should be able to convert from kilowatt hours to BTUs. From BTUs, you should be able to convert into cubic foot of gases. So if we're trying to understand how this is all measured, kilowatt hours is how much electricity. That electricity could be used to measure heat units. Those heat units could be measured by how much gas it takes to make those heat units. This is dimensional analysis, and this is how we put it all together in regards to math. The math is not hard. Envisioning what's going on is the complex part. So if you could get the vocabulary done, then you could do everything else. All right, let's continue. All right, so then we could take this question, if you were taking all of that from previously, and we could do how much gas is needed in a cubic feet for one hair dryer. Once you get how many cubic feet, you're going to multiply that by 1 cent, and then how much does that cost a year? And then basically you would generate a number. All right, I'm not going to tell you that number right now. You guys could generate it on your own. Maybe we could discuss it during class. All right. Now we could take that and say, well, a more efficient dryer uses 25% of that energy. How much energy would you save? Once again, this is dimensional analysis. Great question. Okay. So I would give you a math worksheet, and then we would go over these, and that would be that. All right. Let me focus on something called GPP and NPP. All right. Gross primary productivity and net primary productivity. Gross primary productivity is going to be all of the energy, all of it. Net primary productivity is really what is left over. So let's say, I have a certain amount of energy. Just let's say I have 100 units of energy. However, I'm constantly using that energy due to respiration. And that's basically the term we use for using that energy. So let's just say every day I start my life with 100 units of energy. However, due to my actions, I move, I breathe, I walk around, I think, I'm using 50 units of that energy. Okay? I probably have to eat 50 units of energy a day so I could maintain that perfect balance. So think of GPP is going to be the total amount of energy. You can solve GPP by adding, and it's a math equation, GPP is equal to NPP plus respiration. Or you could reverse that. Respiration plus NPP, net primary productivity, is gross primary productivity. And then you can flip that equation one more time, and you could go gross primary productivity minus NPP, net primary productivity, is going to give you respiration. All right? Be familiar with those terms. We'll fly through this because you probably should have known this already. We have a food chain is a simple chain. If I wanted you to identify the producer, you should be here. If I wanted you to identify the primary consumer, here. The first trophic level, here. The third trophic level, here. All right, top of the food chain, mongoose. Predators, would you be able to do that? Here, 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 okay? Herbivore, okay? Carnivore, okay? This most likely is an omnivore, all right? Know all those vocabulary terms in that, okay? Let's keep going. A food web is more complex. It's going to have multiple relationships and it's more realistic when you think about it. So a wolf will feed on multiple organisms. Now, where does the arrow point? That's the complex part of this. That's where you'll get the questions. So what does the grasshopper eat? And I don't want you to fall on, well, I know that the frog eats the grasshopper. Okay, I don't want you to fall on that because in the AP we wouldn't ask you something. We would probably ask you something more complex, like the fruit fly. All right, what's going on? Or let's look at let's look at one that's a little more complex, the python. All right, we don't know if the eagle's eating the python or the python's eating the eagle in this case. We would know by looking at the directionality of the arrows. The arrows point to where is the energy going. Okay, so if the arrow is pointing towards the eagle, that means the energy from the rat is going to the eagle. So that means the eagle eats the rat. Actually, this means that the eagle eats the wolf. Isn't that crazy? This means that the eagle eats the frog. This means that the eagle eats the thrush. This means the eagle eats the python. Now, I know what you're looking at. You're like, how can an eagle eat a wolf? Well, eagle probably takes a baby wolf. That's what it was. It probably takes a young pup. Okay? All right? So the arrow points to where the energy is going. The butterfly is eating the flower, right? It's also eating the lavender. The mangoes are being eaten by the fruit fly. That is how these food webs work. Another thing happens, or questions that you could think about when you're looking at food webs is, well, what happens if the dragonfly goes extinct? Is the thrush going to go extinct? Well, not necessarily. All right. The fruit flies might actually start coming back in numbers because they're not being eaten by the dragonfly. However, the thrush may now, since it only was eating these two different flies, it only has these to eat, it might actually balance the fruit fly. So you have to understand the relationships that exist when you're talking about all of these different organisms. Some might go up, some might go down, but in reality, they are all going to affect each other. In a food chain, it's more simple. And if the caterpillars go extinct, then everything else go extinct. And of course, that's not realistic. Okay. Okay. I think this is our last slide. Oh my goodness. All right. And this is something called a POP, or something as a persistent organic pollutant. And the movie Dark Waters was explaining a POP. And there was a scary stat that it said, and I don't know if it's true. I want to go check it out. But it said about 99% of the human population has this chemical PFOA in them right now. How did they get this chemical? Well, this company called DuPont made this chemical, and it made it in Teflon and in our pans, and it doesn't break down. And so that means it's going to stay in our body as long as we possibly live. So it's kind of scary. I don't know if it's necessarily true. I will do a check on that. But this is a chemical that does not break down in our ecosystem. Right? It does not break down in our ecosystem. So let's see how it happens. Well, we've created it, and typically a lot of POPs are going to be man-made, aka anthropogenic. That's a vocabulary term. And so we created this chemical that we probably shouldn't have, but it does amazing things. Like Teflon was cool; you could actually cook in a pan and nothing stuck to the pan. It was amazing. However, you were also poisoning yourself. Anyhow, that is going to eventually get into the ecosystem, either by runoff or by waste from the company, and it'll get into the ecosystem. It'll be absorbed by the smaller organisms, like phytoplankton, and then you're going to have zooplankton eat them. Now, look what happens to the concentration of that toxin. They're going to eat a lot of these. Now, the herring is going to eat these. Wow, they're eating a lot of these. So now look at the concentration in the herring. Now these eat a lot of these. Oh my God, look at the concentration in the salmon. And then you can think of, whoa, big mama predator here. And this is a long-lived predator. So by the time this predator dies, it has accumulated many parts of those toxins. And so that overall thing, there's two buzzwords here. One buzzword is biomagnification, and that means as it moves up the trophic chain, the concentrations get higher. And then there's the other term that's very similar that people misconceive and get the answers wrong, is called bioaccumulation. Bioaccumulation is when it's going to accumulate in the tissues of an organism through its lifetime. So this has bioaccumulated many of these toxins. All right. I think this has to go with that question that I asked. How does toxins like PCBs or DDT end up in the blubber of polar bears? Well, it ends up in the blubber of polar bears because the chemical stays in the system for so long. All right. POPs, know the big ones like PCBs, DDT. All right. And we don't use PCBs anymore. PCBs were made in lubricants that we used in transformers for electrical conduits. Basically, if you looked at the electrical posts, those two like things like shaped like that, they get really hot. So we had PCB lubricants in them. When they exploded, the PCBs would end up on the ground. They'd be absorbed. We no longer use PCBs. We no longer use DDT, and we've learned from that. All right. I hope you enjoyed this lecture. I kept it under a half hour.